In this video, we describe how the standard molar reaction Gibbs energy is related to the equilibrium constant of a chemical reaction. Alright, so in the prior video, we have seen how we can calculate the spontaneity of a reaction at any conditions that we wish by simply calculating the sign of this quantity. And again, this is not at the standard state, but under any conditions that we wish, by simply utilizing this equation that we have derived. Alright, so that's just the molar Gibbs energy under any conditions that we wish, which allows us to predict spontaneity, is simply the molar Gibbs energy under standard conditions, which can be easily calculated by thermodynamic tables, and then a correction which depends on the concentrations of reagents and products at the conditions that you're interested in. Now, what we're going to do is try to look for a limiting case of this reaction, which is going to be extremely useful. Alright, so we know that if the sign of this value is positive, then the reaction will not be spontaneous. If we know that the sign of this Gibbs energy of reaction at the conditions that we're looking at happens to be negative, and then we're working at constant pressure and temperature, then the reaction will be spontaneous. And again, these requirements require constant pressure and temperature. But there's another case, which is what happens if the molar Gibbs energy happens to be exactly zero. Well, if this is exactly zero, then we're at equilibrium, right? The reaction is not spontaneous in the forward direction or the reverse direction. Instead, you actually have reached equilibrium. Alright, so again, notice that this will be not spontaneous as written. This will be spontaneous. And then if the molar Gibbs energy is zero, then you are at equilibrium. And again, all this has to happen at constant pressure and temperature, but that's generally how we run our chemical reactions. Alright, so then let's actually take a look at how this equation looks like once you reach equilibrium. Well, if you reach equilibrium, then what happens is that delta RGM happens to be zero. This number doesn't change, that's simply the molar Gibbs energy at the standard state. But then we have something interesting here, and that is that once you actually reach equilibrium, then the reaction quotient becomes the equilibrium constant, right? The reaction quotient is just a more general expression of the equilibrium constant, where you can put any concentrations or pressures that you wish, but once you're at equilibrium, then Q becomes K, right? At equilibrium, this is what happens. So this is an extremely important reaction, because notice that you can calculate something that seems very elusive, like an equilibrium constant, simply from the value of the reaction Gibbs energy under standard conditions. But this is straightforward to calculate. Notice that we have two recipes to calculate. This is just the enthalpy of reaction under standard conditions, or the entropy of the reaction under standard conditions. That's one way to calculate it, right? Using those. Delta RHM standard minus T, delta RSM standard. That is one way to calculate it. And there's another way that is even simpler, which is simply to just take the balance of the molar Gibbs energy of formation of reagents and products, right? So you can do this as well as the sum of the molar Gibbs energy of formation of products minus the sum of the molar Gibbs energy of formation of reagents multiplied by the stoichiometric coefficients. Okay, and this will be standard as well. Right, so these calculations are straightforward because all these values for the molar Gibbs energy of formations, or the molar entropies at the standard state, or the molar enthalpies of formation at the standard state, those are provided in tables. And what that means is that we can calculate this very easily, and what that means is that we can calculate what the value of the equilibrium constant is also very easily. Notice that you can solve this expression for the equilibrium constant, and then this is simply going to be equal to e to the minus delta r gm over RT. Okay? So notice how powerful this equation is, but this is just one of the limiting cases of the more general equation that tells you how the molar Gibbs energy changes with concentration. Right? So to solidify this knowledge, we're now going to run a numerical example for a particular chemical reaction to see the power really conveyed by these expressions. Right, so then let's take a look at the formation of dinitrogen tetroxide from nitrogen dioxide, which is a benchmark or a textbook reaction in the gas phase, right? So this is what we're looking at. Two molecules of nitrogen dioxide condensing to form a dimer, which is dinitrogen tetroxide. And this all happens in the gas phase. Right, so the question here would be, please calculate what the equilibrium constant would be at 298 Kelvin. Alright, so notice that what we can do is take this reaction, and then at equilibrium what will happen is that 0 is equal to delta RGM plus RT natural log of K, that is what happens at equilibrium, and then K therefore is equal to E to the minus delta RGM over RT at the standard state. Right? So we know what the temperature is, 298 Kelvin, and then we simply have to calculate what the molar Gibbs energy is at the standard state. Alright, so this, again, you have two recipes. You can use the enthalpy of the reaction, then the entropy of the reaction, and combine them using delta RHM standard minus T delta RSM standard. Or you could use the Gibbs energy of formation of these two species and combine them as well to get exactly the same number. We're actually going to go this route instead, just to show what the values of the enthalpy of the reaction and the entropy of the reaction would be. Alright, so again, this could be calculated by just taking just the balance of the enthalpies of formations of products minus reagents, and that value happens to be equal to minus 58.0 kilojoules per mole. Okay, so this reaction is exothermic because you're forming a new bond. Okay, now you will have here minus 298 Kelvin, and then the entropy of the reaction. Notice that here we're turning two gas molecules into just one, so that is going to lead to a loss of entropy, and therefore you expect the sign of the reaction entropy to be negative. And it is. This reaction entropy happens to be minus 178 joules per mole Kelvin. Notice though that because here you have kilojoules per mole, but the reaction entropy is in joules per mole Kelvin, you do have to do a unit conversion there to make sure that all units are in either joules per mole or kilojoules per mole. Alright, so actually this number happens to be minus 176, not 78. So the conversion would be minus 0.176 kilojoules per mole Kelvin. Right, so now you have everything in the right units, kilojoules per mole in this case, and then notice that this will give a negative contribution to the Gibbs energy at the standard state, but that is going to be a positive contribution to the Gibbs energy. Anyways, when you put them all together, this happens to be minus 5.6 kilojoules per mole. Alright, so what that means is that the reaction is going to be spontaneous under standard conditions. And that means that the pressure of this is 1 bar, and the pressure of this is also 1 bar. Okay? Now we can also calculate what the equilibrium constant would be by just following that equation, right? So this is going to be E to the minus reaction Gibbs energy, which in this case is 5.6 kilojoules per mole. Alright, so it will be minus that number, so that would be a positive number, and then divided over RT. And here we have to be very careful about units. Notice that when you calculate delta G or delta H, those are kilojoules per mole. But here you have to use R, and that means that you will be using R as 8.314 joules per mole Kelvin. Right? So there's a kilojoules to joules transformation that you need to carry out right there. So don't forget to do that. And a way to avoid making this mistake is to always write the units after any quantity that you have in problems, right? So 5.6 kilojoules per mole will be 5.610 to the 3 joules per mole. Now you can write your 8.314 joule per mole Kelvin, and the temperature is 298 Kelvin. And when you do this, it turns out that the equilibrium constant is 9.6. Okay? Remember that the equilibrium constant will be the pressure of N2O4 at equilibrium divided over the pressure of NO2 squared at equilibrium. Okay, so let's see if we can wrap all this up. Notice that this equilibrium constant means that this process at 298 Kelvin is displaced to the right because you have more products than you do reagents, right? That is provided by this ratio of pressures. At the same time, this value is actually dictated by the value of the reaction Gibbs energy at the center state, which happens to be negative, and that means that the reaction, it is spontaneous from left to right if the concentrations happen to be 1 atmosphere for all of them. Right, so that makes perfect sense. If you have here one atmosphere of pressure and 1 atmosphere of pressure, but the equilibrium constant happens to be 10, it's obvious that the reaction is going to be spontaneous left to right, not right to left, right? So that is all of the information that is connected right here. Now, following this reaction here, now that we know what the equilibrium constant is and what this number is, notice that we can in principle compute whether the reaction will be spontaneous under any partial pressures that we wish, right? Suppose that you have now 100 atmospheres here and then 1 atmosphere here. Would that be spontaneous? Well, you would simply need to operate through here and calculate the sign of delta G, right? So notice how powerful this relationship between the Gibbs energy and the equilibrium constant or reaction quotient is. It allows you to do a lot of things. Calculate spontaneity under any conditions that you wish, calculate the equilibrium constant, and predict whether the reactions will be displaced from to the left to the right, and so forth, just using thermodynamic tables, right? Ultimately, everything hinges on this value, but that is very easy to calculate simply from thermodynamic tables.